Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today I would like to have a class with the topic of kinetic theory of gas. Before I start the class, let me introduce myself. My name is Jaslin Ihsan. I was graduated from University of Yogyakarta State University in 1992, and then directly in 1993 I was appointed as a lecturer in the university in the Department of Chemical Education. I pursued my studies to get Masters of Applied Science in Lathrop University, Australia, and finished in 1999, and then I pursued my study in the same university in Lathrop University, Australia, and graduated in 2004. The class today I would like to discuss with you together is about first gas pressure, translational kinetic energy, and root mean square speed. Everyone here I think knows exactly that the gases is very important. No one can deny this. For example, in our life here every day, everywhere, when we step on our feet, and exactly we need oxygen to breathe in. This is the example. The another example is helium gas is used to fill a birthday balloon, and also the steam formed in the air during a hot shower is also the gas. So gases are one of the most pervasive aspects of our environment on the earth. We continually exist with constant exposure to gases of all forms. So also the example that a windy day or a still day is a result of the difference in pressure of gases in two different locations. A fresh breeze on a mountain peak is a study in basic gas laws. So the gas is actually very important in our life. This is the way that gases is one of the topics that is very important to be learned. Especially for today, we would like to discuss about the kinetic, the theory kinetic of the gas. Just imagine that this is the gas in a container or in a room. You can see blue and red one. So two kind of molecules just represented by two different color of balls. So what you can describe about the gas from this picture? Just have a look first from the movement. So first what we can conclude is that gases is always move. Gases always move all the time. First. And so you can see the speed of the gas. Do you think that the gas move in the same speed? The answer is no. Gas move not exactly in the same speed. So this is first. And second. Third, you can see that between the gas collide each other. So collision happen between the gases. In this moment, we assume that the collision is elastic. Fourth, what you can see over there is that because they move all the time, the distance that the gases pass is exactly very long, very far. So the size of the molecule of the gas is assumed very small compared to the distance that the gases can reach. So this is the assumption when we learn about the kinetic theory of the gas. First, gas consists of large number of small individual particles with negligible size. So the molecule, as I mentioned earlier, that the size of the molecule is very small, especially compared to the distance they achieve because they move all the time. Secondly, the particles always move in random motion and they collide. And no forces exerted among each other. So the collision is inelastic. They do not react each other. And because they not react and they collide in elastic, so the kinetic energy directly proportional. So here, kinetic energy is directly proportional to temperature in Kelvin. I think you know that. With the equation is like this, represented by, you can see here. I think you learned this at senior high school in first semester, second semester, earlier semesters. In the ideal gas law is written by P times V equal to N times R times T. P is the pressure, V is the volume, and we know N is number of mole of the molecule, and R is the constant, gas constant, and T is the temperature in Kelvin. And the number of moles in the ideal gas, as you know, is equal to the number of the molecule divided by Avogadro number. And I think everyone knows too, you know exactly the Avogadro number is equal to 6.02 times 10^23 per mole. And the gas constant R is equal to 8.31 joule per mole Kelvin. Now we go a bit further about pressure and temperature. Pressure occurs because of collision of the molecule on the surface. So, as I mentioned previously, that the gas, just imagine in this room, it just always move and move. They move to the right side, to the left side, up and down, and they reach and collide to the surface, and this result in pressure. And we know that pressure equal to the force divided by the area of the surface. So forces divided by area, and forces itself is equal to dp per dt. And that one is called the rate of momentum given to the surface. Momentum is given by each collision times the number of collision in time delta t or dt. So here we can say that only molecule moving toward the surface hit the surface. And assuming the surface is normal to the x-axis, half of the speed move toward the surface. So just imagine that the surface is on the direction of x-axis and the gas just move toward the x-axis with the speed of v and hit the surface. So the speed we call Vx with index x. And because they move toward and move away from the surface, so we count that the number of molecules hitting the surface is only half. Only those close enough to the surface hit in time delta t, those within the distance Vx time dt. So this is, imagine that this a container of the gas and put on the wall with the surface area equal to A. And you know that the distance or the length of the container is equal to Vx times dt. Vx is the speed on x-axis direction. So we're just assuming that here we just only see the gas move in x-axis direction. Okay, and then the length of the container is equal to the speed times the time delta t, and then the volume of the container is equal the area times the distance times the length of the container. So we can say that any molecule of the gas with the volume of A times Vx times delta t must hit the wall, must hit the surface. Then we can say that the number of collision hitting an area A in time dt is equal to half time n bar v times A times Vx times dt. Here A is the area of the surface, Vx is the speed on the direction of x-axis during the time delta t. And n bar v, we call it the molecule density, and the number half is because total particle hitting the surface is only half, because half toward the surface and half of the molecule move away from the surface. So this is average density of the gas. And the momentum given by each collision to the surface is equal to 2m Vx. M is the mass of the molecule and Vx is the speed of the molecule on the x direction. So here momentum in time delta t is given by, represented by this equation. So very clear, I think. And the force, as given earlier, that F force equal to dp per dt. So then we get this equation: 2m Vx times half time average density times surface area and times the speed of the molecule of the gas. And the pressure itself, you know, is forces by the surface area, and meaning that this equal to average density of the molecule times the mass of the molecule times the speed squared. In the earlier of this class, I said that not all molecules have the same speed of Vx. So here then easier, we just write it the speed by Vx squared with the bar meaning mean. So here the pressure then written by and by V meaning that is average density of the molecule times the mass and times the average speed of the molecule squared. I think everyone understand. So if you have any question, just okay. So here, because the as you know, the direction of the gas is not only to the x-axis, but also the y and also to the z-axis, mean to 3 directions. So meaning that the speed x squared here is equal to only a third of v total squared, total speed squared. And the speed total speed is equal to here Vx plus Vy plus Vz. So meaning that average speed square is equal to, average speed square is equal to a third of speed square. So then here the average speed square, we call it V square. V RMS, root means square. It is hard to pronounce, but you can see in the presentation over there that Vx squared with the bar, meaning that this is average speed square, is equal to a third speed RMS square. And here speed RMS meaning the root means square speed and written as on the presentation. So the pressure here is clearly can be shown as P equal to that. And you can see the average translational kinetic energy is also given on the presentation. I hope that you can catch what I say, because here is all numbers and all equations, sometimes giving us difficulties to catch only by listening. So that's where you need to always see on the presentation and look at very carefully and understanding. When you not understand what I'm saying, you can just giving me message or just writing by chatting on the web or by online, and I can explain a bit further to you about it. So pressure can be written as here, and from the ideal gas law can be written that kinetic is like that. So we can then count the Boltzmann constant is equal to that one, and the value of the constant is 1.38 times 10 minus 23 joule per Kelvin. And from the question and that one, we can see, we can conclude now the speed RMS root mean square speed is equal to the square, sorry, the root square of 3 times R times T divided by N. And here R is the gas constant, T temperature in Kelvin, and M is molecular mass. And molar mass is actually mass times the Avogadro number. So then here we can say the pressure is actually density times kinetic energy, and temperature is proportional to kinetic energy. Meaning, from the previous equation, we can see here that the kinetic energy is actually depend on the temperature. So I think this about the class today. Next, I think is the assignment that you need to do. First, compute the root mean square speed of a nitrogen molecule at 20 degrees Celsius. At 20 Celsius degrees, at what temperatures will the root mean square speed be? Half that value and twice that value. So you can write down this question and just do it by yourself. You can discuss with your friend, of course, but you need to understand based on the explanation I have given to you just previously. So using this, of course. Next question is, please estimate the root mean square mean velocity of mean speed of hydrogen gas. You can write down the question and answer it later on. Third question is, what is the average translational kinetic energy of nitrogen molecule at 1600 Kelvin? First in joule and B in electron volts. That I think the class today, and we will continue in the next kinetic energy in the second part about the Boltzmann distribution. Thank you very much for your attention. Please feel free. Ask the question if you have any difficulties. Just don't hesitate to contact me by email or meeting me in our office in the lab of chemistry in Yogyakarta State University. And thank you very much. Thank you.